Good morning. I am Ridla and I will be presenting my mini project titled Early Crop Pest Detection Using Image Processing and Computational Intelligence under the guidance of Dr. K. Deepika Madam, Assistant Professor. This presentation includes the core components of the project, that is, abstract introduction, literature survey, existing system, proposed system, modules, methodology, system architecture, dataset details, module architecture, test cases, results, conclusion, future scope, and reference. Abstract. Pests are the serious threat in agriculture. While pesticides are commonly used to tackle infections, overuse can harm the environment. In this project, we aim to develop an intelligent system for early pest detection using image processing and deep learning. By acquiring leaf images of infected crops, then converted them into grayscale, extracted features using the image process, and then classified them using the VGJ16 to identify pests. This automated system helps the farmers act as the early and reduce pesticide dependency. So, the agriculture supports nearly 70% of the Indian population. However, the pests can severely damage crops, reduce yield, and threaten food security. Manual pest identification is inefficient and inconsistent. That's why the proposing using the digital image processing and machine vision to automate early pest detection. This technique helps in monitoring crop health and the more accurately and consistently than the traditional methods. Literature survey. Early detection of the pest in the crops plays a critical role in sustainable agriculture. The image processing is at the core of the project. We analyze the leaf image using the various features such as the color features, texture features, shape features. Color features detects the discoloration between the which might indicate the chlorophyll loss due to the pests. Text features help identifying the patterns like rough patches or web-like signs of mites. Shape features recognize the irregular shapes or the holes that suggest the pest chewing. The several studies have demonstrated the success in pest detection using the image processing. For instance, the Bang et al. Used the convolutional neural networks to identify the infected apple leaves. Lee et al. Proposed the deep learning based approach using the for wheat disease segmentation. Computational intelligence includes ML and DL. So these models are trained on the large data sets of healthy infected crops images. So the machine learning helps in identifying relation between the image features and the diseases. Deep learning, especially the convolutional neural networks, automatically learns features and often provides higher accuracy. This combination helps in the build of a robust, scalable, and automated pest detection. This Patel et al. Predicted the soybean diseases using the environmental data and machine learning. Zhou et al. Applied the fuzzy logic to the detect aphids in cotton leaves. By integrating both the image processing and computational intelligence, for example, this Zhang et al. Built a hybrid system for the citrus pest detection, as the Khan et al. Combined the computer vision and machine learning to monitor tomato crop pest in real time. proposes system which detection of the both type of pest and the disease. It minimizes the human error and offers accurate prediction using the deep learning, especially VGG16. This helps farmers take the action before pest and cause significant damage. The core modules of the project: the upload the pest images, dataset is uploaded to the application, pre-processing database, images are converted to the grayscale, normalized and split into 70% of training and the 30% of the testing sets. Run algorithm. VGG16 model is trained on the datasets. Test image prediction. A new image is uploaded and the model predicts the pest. Methodology: capturing image capturing, acquiring the images using a digital camera, pre-processing, converting the images to grayscale and resizing of the image. Feature extraction: extracting relevant images and classification. Detection, classify and prediction, predicting the pest using the trained model. System architecture: capturing the leaf images from the crop, which are the tomato, bell pepper, potato crops, acquiring these images and storing them in a data sets. Then the image pre-processing and the feature extraction, we classify the image. This system then predicts whether the leaf is healthy or affected and identifies the pest if it is present. Dataset details: so the total number of images are 358, which are potato are 111 and tomato 218, bell pepper are 23, and the model is trained based on the 70% of training set and 30% of testing, which are splitted, and it is based on the 3 crops and 15 classes, which are 14 diseases types and 1 is healthy class. VGG model architecture: here it is a deep convolutional neural network which has the input layer, convolutional layer, max pooling layer, fully connected layer and the output layer. Input layer accepts the image of size 224 into 224 into 3, which pest affected crop leaves are resized to the dimensions. In the convolutional layer, 13 convolution layers are used. Uses small 3 into 3 filters to capture the fine details fine details of the image. Each convolutional layer is followed by the ReLU activation to introduce the non-linearity. In the max pooling layer, after the every 2 or 3 convolution layer, 2 into 3 max pooling layer is applied. It reduces the spatial size of the future maps, helping in dimensionality reduction and faster computation. Fully connected layers: after the future extraction, the model has 3 dense fully connected layers. The first 2 fully connected layers have 4096 neurons each. The final fully connected layer has the number of neurons equal to the number of classes in our data set, which has the 15 classes we have. So the 15 neurons it has. And the output layer uses a softmax activation function to output probabilistic for each class. The class which highest probability is the predicted label. The test cases: the scenario we have a VGG16 model trained on a dataset with a limited number of classes, 10 classes. We want to test the model's performance when the increasing the batch size during the interface. So tested the model under the varying parameters such as the increasing batch size and the number of classes. The goal was to evaluate the model sensitivity and accuracy under the different conditions. The system performed consistently well, confirming the robustness and the VGG16 for the pest classification. So the results in output package, we can upload the image into it and click the predict button. We get the results. The model could successfully detect and classify the diseases, tomato early blight and the pepper bell bacterial spot. If it is a no disease on the leaf, we get the no disease detected. It is a early leaf. The more diseases. The prediction matched the ground truth tables with the high accuracy. With the results were validated using the confusion matrix and the accuracy matrix, the promising outcomes for the real world application. This project demonstrated that combining image processing with the deep learning leads to an efficient and scalable solution for the early pest detection. This system not only reduces pesticide misuse but also empowers farmers to act on time, resulting in better crop health and the yield. For the future scope, adding a real-time monitoring using the IoT technologies such as sensors, camera, and extending the system to more crop types and the pest variables, and optimize the models to run on mobile devices for the field use. And these are the references. Then coming to the demo, here we are running. So here is the output page. We have to select a file from here. We can upload a image. Now clicking on the predict button, we'll get the output. Here is the leaf have the tomato early blight disease, and here is the treatment for this. Thank you.